Welcome to Move to Learn, the Handspring webinar series for manual therapists and movement educators. Today we are thrilled to welcome two expert authors, pioneers, along with Dr. Stephen Levin of the field of biotensegrity. Our first author is Susan Lowell de Solo, the author of Everything Moves, and Graham Scarr, the author of Biotensegrity, the Structural Basis of Life. Before this captivating presentation from Susan and from Graham, let's take a look at the slide that explains how things work, how to participate in this webinar. The webinar will comprise roughly 45 minutes of discussion, presentation, and guided practice, followed by 15 minutes of Q&A. The chat is on, so do say hello and tell us where you're joining from, and perhaps also let us know your experiences with biotensegrity. We welcome your questions, so please submit those using the Q&A button on your screen. At approximately 15 minutes to the hour, Susan and Graham will begin to answer your questions. If there are additional questions, they are happy to stay another 10 minutes past the hour. We are recording this webinar and will share a link to it in our follow-up email. This webinar is streaming live on YouTube, and we have a disclaimer, just a recommendation that this discussion is for informational and illustrative purposes only and is not meant to impart medical or therapeutic advice or instruction. I'm delighted to give to you the brief bios so that you'll be introduced to our esteemed authors. Susan Lowell de Solo has an MA in Human Development and Education with a focus on kinesthetic learning and is certified as a Level 2 Tai Chi instructor by the American Tai Chi and Qigong Association. She is a certified flex-aware teacher. Since 2012, Susan has been an associate of Dr. Stephen M. Levin, organizer of, or an originator of the founding of the theory of biotensegrity. Susan is a co-founder and head organizer for DC BIG, which is the Washington, D.C. Biotensegrity Interest Group that was established in 2012. And she is a co-founder of the Stephen M. Levin Biotensegrity Archive. Her co-presenter and also expert guest author is Graham Scarr, author of Biotensegrity, the Structural Basis of Life. Graham Scarr is a retired osteopath, fellow of the Society of Biology and fellow of the Linnean Society, and has a particular interest in the mechanics of living structures. Fascinated by the numerous examples of geometric patterns and shapes in nature, he has been researching their significance over many years. As a graduate in microbiology, and after spending several years developing his skills in the bacteriological research lab, he is now part of a special interest group looking at the significance of the biotensegrity concept to biomechanics and clinical practice, and at the forefront of current thinking about this subject. Working closely with Stephen Levin, an orthopedic surgeon who first recognized the importance of the biotensegrity concept for living organisms, Graham has developed new methods, new models that progress our understanding of the structure, function, relationships in human biology, and published several papers on the subject in peer-reviewed scientific journals. Susan and Graham, welcome to Move to Learn. We are in for a treat with the presentations.
Hello. Hello, Elizabeth.
Thanks, Elizabeth.
Susan, would you lead off with an experience so that the participants, the viewers, have a kinesthetic appreciation of biotensegrity.
Sure. And I just want to say I've seen a few things pop up in the chat, and I just want to say hello to friends new and old that I see that are here today. So that's wonderful. When we're learning about biotensegrity and we're trying to apply that understanding to our own bodies, we're learning about nature's pulls and pushes and all at all tiny little scale levels through the system. So one way you can begin to play with that understanding of those balances is if you take a weight like a book and balance it on your head, you're essentially turning up the volume in your internal force management system. And then little tiny moves this way and that, you can begin to feel, am I in a sustainable place where the effort is distributed? Okay. And then if you find a way to do things where maybe there's more tension generated, you can sort of see if you can resolve that some way. And it's just a fun thing to do to begin to feel those internal multi-scale level pushes and pulls.
Susan, I disappeared from the screen so that people could appreciate the book on the head. Going forward, how about this gorgeous video that you've prepared that explains the background information we need for the topic?
Sure, thanks.
Tensegrity, biotensegrity, and applied biotensegrity. Tensegrity structures are pretty new, and they're really unique. Phil Earnhardt says this is only the second way that humans have ever figured out how to build, and this is after hundreds of thousands of years of human culture. These structures have a oneness that somehow emerges from this duality of struts that resist being pushed and cables that resist being pulled. And what you really have to do is build a tensegrity if you really want to understand these. Once you build one, you can feel it, you can experience it, and you can let its unexpected behaviors surprise you. The Wyss Institute at Harvard University says that tensegrity is a fundamental determinant of all living systems at all size scales, and they call it the architecture of life. So, a lot of people are looking at this. It's important to distinguish between tensegrity as a structure and tensegrity the word, because people get really confused. And it's easy to see why. The structure has, any tensegrity structure has two components, the struts that are under compression and the cables that are under tension. But tensegrity, the word, also has two components. Those two components are tension and integrity, two different words. And Buckminster Fuller combined them in something called a portmanteau, which is an invention. And so he made up the word. But a tensegrity is not made out of tension and integrity because those are not building materials. Tensegrities are systems, and the movement that they exhibit is omnidirectional, it's helical, it's unexpected, it's auxetic, and everything moves instantly everywhere. So that's tensegrity. What's biotensegrity? And biotensegrity is the theory of tensegrity architecture in biology. We're talking about all living organisms from viruses to vertebrates, their systems and subsystems. Tensegrity and biotensegrity, these are pure sciences, natural sciences. We're just having the goal of trying to understand what it is we're trying to learn about. We're not trying to do anything other than understand it. So if that's tensegrity and that's biotensegrity, then what is it that's sort of the elephant in the room, as they say? Most of the people who are the early adopters of biotensegrity, they may be biotensegrity aware, biotensegrity inspired, but they do have a goal. They're trying to invent something, or they're trying to innovate. They're trying to develop practical applications. So they are trying to solve problems by understanding biotensegrity. And what we've done is we've started to call this applied biotensegrity. So anybody who's studying biotensegrity with the purpose of trying to improve clinical or practical applications, improve movement practices, therapeutic techniques, anybody who's using it for any kind of problem solving or invention, engineering, this all falls under the category of this biotensegrity inspired applied biotensegrity. But then we also have the category of that which is just biotensegrity inspired. It's not trying to solve any kind of problem. It's just exploring. And for the sake of exploration, this would be the sort of artistic ventures that we're seeing. And we've seen everything from volumetric poetry to dance performances, of course, sculptures. So these are our categories. And so when we're trying to figure out and talk about the work we're trying to do, these are the 4 categories we're using. Of course, you can't apply biotensegrity if you don't study biotensegrity as it is as a pure science, and you can't really study biotensegrity without an understanding of tensegrity. And these things tend to sort of flow back and forth. We who study this tend to kind of flow between these different categories of study in order to round out our work and improve what we're doing. So that's what we've got to share today. And I want to thank you so much. Please come and visit us on YouTube or at the Biotensegrity Archive website. I'm Susan at biotensegrityarchive.org. And please join us on Fridays for our Biotensegrity tea parties, which are streamed to YouTube. Thanks.
Susan, that video that you've created provides such a rich foundation and such a clear foundation of a phenomenally complex field. And now, based on that foundation, can't wait to hear how you and Graham are going to lob back and forth about additional details in the field.
Well, thanks, Elizabeth. And let me just mention, for those of you who don't know me, these are my reading glasses. They just help me see more clearly. They've got little holes in them. So that's what I use. And so one of the words I mentioned in my presentation is this word auxeticity. And people kind of, what? We're not trying to be mysterious here. But it is a useful word because it's one of those unusual properties that we see in tensegrity structures. So I'm going to throw this over to you, Graham. You ready? 1, 2, 3. From Washington, D.C. to Nottingham. catch.
Oh, thank you. Thank you. That was amazing. Thank you, Susan. Well, before I move on with my presentation, I want to show you just one of the characteristics of tensegrity that makes them interesting and relevant to the human body. Here is a 6-strut tensegrity, the basic tensegrity structure, the simplest omnidirectional structure. It's called a tensegrity icosahedron because the ends of the struts, they correspond very closely to the icosahedron, which is one of the platonic solids with 20 sides. Okay, that's a bit of geometry out of the way. The thing about this tensegrity model is that, let's see, I can move it and you can see the thing moving very slightly, but it's actually expanding and contracting in every direction. Now this displays auxetic behavior. This is very unusual in man-made structures. There are very few man-made structures that do this. Becoming more, but tensegrity is one of the defining characteristics of it. And I'll show you this other model here, not a tensegrity, but it shows how the entire structure can expand and contract in every direction. For the technically minded, it exhibits a negative Poisson ratio, but we won't get too deeply into that. Negative Poisson.
Hey, Graham.
Hello?
Graham, I'm going to interrupt you. Can you show that jitterbug again just for a second?
Right,
Folks,
yes.
I want you to think about your breathing when you see this, that your lungs are expanding and condensing all at once in all directions. That's just a little model that helps us feel that. Thanks, Graham.
That's right, that's fine. Yes, and this auxetic behavior is also described be found in skin, tendons, cells, most of the visceral organs. So it's a very important characteristic to take more notice of. Okay, if we start my my video now. If it was a machine, it uses engineering principles to do that. But when we look at these pictures, they look anything but machines. The picture on the left particularly, we're all being told that the spine, the vertebral column, keeps us upright in its vertical position. But here we see that one of these chaps has a horizontal spine and it's functioning perfectly well. And of course, most animals have horizontal spines, which are not really that different to humans. But in the middle picture, the human body can support the entire weight just from the tensional network around the shoulders of the lower person. And most of us are familiar with dancing. We've done it at some point in our lives. A simple movement with enormously complex control mechanisms to make this happen. But we can do all these things with ease. So next slide. Now, we've all been told that the body is held together by a system of hard bones and a skeleton. And the muscles move the bones and cause movement. And the joints move. The bones move through a system of joints that work like a lever system. Next slide. But the problem with levers is that they generate bending moments and shear stresses and stress concentrations. And it is most unlikely that developing tissues would be able to withstand disastrous consequences of these. Levers rotate around fixed fulcrums, yet bones follow complex helical pathways during motion. In addition, the nervous system is incapable of controlling the huge complexity of joint movements on its own, which thus leaves a massive gap in our understanding. Next slide. So the human body is a global heterarchy, and I'll explain what this term means. We are all familiar with the word hierarchy, where we have large important structures at the top, followed by smaller, less significant ones below. So a top-down hierarchy where the top-down things influence everything below it. And this is the way that anatomy textbooks are written. But the human body actually exhibits a heterarchy, where each part is made from smaller parts, which are made from even smaller parts. But each one has an influence on all the others at every size scale. The large ones influence the small ones influence the large ones, and across it at every size scale. Next slide. Now I'll read the caption for here. Fascia the tensional network enclosing compartments under compression at multiple size scales. Now, it is very difficult to draw a picture of the fascia, which is enormously complex, pervades our entire body. And most people think of it as this fibrous network under the skin that we can often feel and move with our hands and can see it in dissections. But it's important to mention that this tensional network is enclosing these compartments. The compartments can be the thorax, the abdomen, the cranial cavity, or smaller level bones and muscles and organs such as the liver, the heart, the lungs. At a smaller scale still, we have glands and blood vessels and nerves. And keep on going down, then we have cells, all of which provide a compressional element, often mostly containing proteoglycans tightly bound with fluids or water that makes the system into a tension compression network, defining characteristics of tensegrity. The next slide, please. So here's that basic tensegrity model, the tensegrity icosahedron, where the struts or compression elements are suspended or appear to float within the tension network of cables. And the same principle operates in the human body. The tension elements, the compression elements, are formed through the balance of forces flowing through them during embryological development, as well as chemicals, electrical influences as well. So each structure is a physical representation of invisible forces. So you won't see this model in the body anywhere, but it's a representation shown in this right-hand picture of those interacting forces that display themselves in what we call bones, the heart, skin, everything else. So that's a quick introduction to tensegrity from my part, and I'll see you shortly, and back to, I think, Susan as well.
Thanks, Graham. When Dr. Stephen Levin, affectionately known as Steve or Uncle Steve, first had this insight when he saw the Needle Tower in Washington, D.C., and he was thinking about it in terms of how dinosaurs move. You know, we saw this amazing tower that I had pictures of in my presentation, and he thought, okay, but then how does it move? And so this sort of idea of how something can move and transform is something that we look at, and we do it through closed kinematic chains that Graham will show you more about. But I want to show you a 4-bar linkage, a little closed kinematic chain in your own body. One line is going to come across your wrist, and then down either side of the arm, your radius and ulna bones. And then just think of that whole system around the elbow as being the other line. And then put your hand there and feel your bones inside as you pronate and supinate, okay? So just as you move your hand around, let's see that other slide, you can imagine maybe this very macro level, large scale level 4-bar mechanism that's an easy one to see and feel right in your body. And I think, Graham, you've got a more complex way of showing it and talking about it.
Yes, thank you, Susan. We'll have the slide back on, please. Just come in again, here we go. There we go. Now, some of you might be wondering, well, why are we using these simple models to display an enormously complex structure like the human body? Well, tensegrity and the human body are based on some first principles of self-organization. And these extend from the smallest of molecules to the complete organism. So we're using these models to illustrate particular points, having a quick skim through of the subject. So here we see some tensegrity models, and the picture in the middle is one of the elbow, the right elbow, showing the upright humerus, the ulna and the radius, and some of the muscles appropriate to this particular description I use in this paper here. Now, every surgeon knows that bones in a joint are not heavily compressed together. Of course, they have cartilage on their articular surfaces, but they're usually just lightly touching, or even sometimes maintaining a certain amount of separation between the bones. And this separation is often visible and has been well described. So the picture on the left is a tensegrity model of the elbow using the same 6 struts again, but slightly modified. And it demonstrates flexion and extension, where the bone can remain separate. Near the picture on the right, a different tensegrity model of the elbow, which has now been taken up by NASA and used in the development of new types of prostheses, potential medical applications. So tensegrity has enormous potential in many directions. The next slide. Now, as Susan mentioned, closed kinematic chains. And the simplest arrangement, well, let's say the closed kinematic chain, which are widespread in engineering, but they're also ubiquitous in biology and form the basic mechanics of the tensegrity model. And as Susan showed, a 4-bar mechanism, which is the simplest arrangement that allows the structure itself to control motion. Now, so this picture on the left, if we move one bar, one of these blue bars, which could be a strut or a cable, in relation to each other, the whole system will move as a unit. So each bar controls the position and motion of all the others. And the same principle happens in the tensegrity model, where you can see white triangular shapes, which are 3-bar shapes that provide stability and allow the blue dotted 4-bar to change shape in a controlled way. Everything that moves is related to every other part, maintains dynamic stability. We have this, the next slide, please, Hilary. But of course, living structures are complex. And although this system might look like just a complex lever system, this is misleading in a biological context, where each part is made from smaller parts. Next slide. Which are made from even smaller parts, part of a complex hierarchical organization. The next slide. Where one part moves, everything becomes involved. So this is partly what got me into it in the first place, where I was working in my patients. I'd be working on one part of the body and the patient report things on the other side. I worked on a shoulder, they report they could feel things going on in the right hand knee. And I thought, what's going on here? Suddenly, for me, biotensegrity explained this interrelationship between everything in the body. And the next part, next slide, please. So in anatomy, we have closed kinematic chains in the knee, where the cruciate ligaments form this conversely cross 4-bar that guides motion of the femur and tibia in relation to each other. And the next slide. In the limbs of horses and humans, these 4-bar systems have been applied there, also been described there. Now in these pictures here, the multi-articular muscles that cross more than one joint, like the hip and knee joint or the knee and ankle joint, they act together. So we have what we call the flexor muscles and extensor muscles working. It has been thought they work antagonistically. This is a huge simplification because, of course, there's many more muscles involved in any movement. But it illustrates the point about the 4-bar mechanism. This is particularly important if we want to say, if you want to jump from a standing position, most people generally can't go very high. But if you crouch down and then jump up, we're using the muscles that cross both the hip and knee joint to transfer their power down to the ankle and foot and enable a much greater range of motion. And the same principle applies throughout the body. There are so many instances of people doing things that performing movements and feats of power that are totally unexplainable. This closed kinematic chain mechanism explains how this can happen. The next slide, please. Another example of this is in the fingers. This is the middle finger. So we have the metacarpal and the 3 phalanges with the 3 joints in the middle. And there are simply not enough muscles to control all these different finger positions on their own. And certainly no extensor muscles in the fingers, because they are contained in the forearm and hand. So what happens is the fascial tissues at very microscopic level and also visible, which are these these blue lines you can see around the finger, huge simplifications, but they process the information of force and direction from the muscles and tendons and then perform their own logic computations that switches the system between different functional states. It allows the fingers to change position in relation to each other in a controlled way. It is a structure itself that is controlling motion. And these closed kinematic chains have been described since the 18th century, of which this was one of the first descriptions by Winslow, the British anatomist. So the structure itself is controlling motion, but it's also acting in synergy with the nervous system. It's not one or the other. The two are operating together. With a biotensegrity system, when we get one motion in one place, mechanically, it can influence something else at a distance away almost instantly, which is why it makes it so important. I'll give a quick example in the temporomandibular joint, where we eat away quite happily, and then one tooth strikes a nut, and quickly the whole system has to change itself to the perturbations within the system. Neurologically, that's enormously complex to organize. Through tensegrity, it's relatively simple. So next slide, please. So here we are again, biotensegrity, the balance of invisible forces. And as I said, human body is not a machine. It doesn't conform to the standard engineering principles. This living structure are formed through what is called soft matter, which is a newly emerging field of physics that governs the behavior of fibers, colloids, emulsions, surfactants, liquid crystals. It's a completely new field. It's been around for about 20 years perhaps, but we need to consider these things, and most engineering science really hasn't caught up with it. So biotensegrity fits in with all that perfectly. As I mentioned before, when one part moves, everything moves. The next slide, please. And finally, for my bit, biotensegrity is a superstability hypothesis for biology. Now, the human body remains intrinsically stable. We can do almost anything to it, and it keeps on going. And mechanically, the superstability tensegrity hypothesis, which is relatively new, and we'll be hearing a lot more about this in the very near future, I hope. So this is a quick final little picture to say by Chris Clancy showing the tensegrity model and all some of the possibilities that will come out of it. So back to you, Susan.
All right. Now, I think, Elizabeth, we had maybe one more exercise we were going to fit in, but we also want to talk about, before that, we want to talk about the concept of systems. And Graham talked about soft matter, really important. Let me just say, if you do any cooking at all food and all living material is soft matter. So it's the reason that your egg whites can get as hard as a rock or as fluffy as a meringue. So I'll just say you've already got a lot you know about soft matter without going into the details. The idea of a system is when you take different parts and then once they're put together, they become something else. Now, you see this all the time. Maybe, Hillary, I could get those slides. Think of a tree. The way a kid will draw a tree in a picture, of course, it just sticks up from the ground. But we know that the roots under the tree are the thing that allows it to not fall down. This is from Ramon Llull, the Blessed, who is a monk. This is from like 1245. But you can see this understanding of the tree with its roots. He would use this as a model for other things. And here's another picture of a tree with roots here in Washington, D.C. that I took a few years back. And we can feel rooted in our own bodies, right? We can have this imagining of roots, and that allows us to be able to stand and move. And we begin to see things as systems, right? When you see things as systems, which is one of the things we study in biotensegrity, it changes your perception. And I know that a lot of you out there are manual therapists, movement therapists. You already know through your fingertips, through your own movement, that everything affects everything else, and that there's a quality of oneness to the body. So just Elizabeth was saying, well, where do we see this in the research? Well, let me just say that I think since the 1600s, this is how the lymphatic system was mapped in the body. Okay, so even though people were saying, well, no, I feel things up here going on, this is what they found anatomically in cadaveric specimens. Therefore, this was the lymphatic system. But about 5 years ago at the University of Virginia, they found the connection that went up into the head. And the researchers, I'm just going to read you this quote. This one professor from the Virginia School of Medicine, Josh Barney, said, I really did not believe there were structures in the body that we were not aware of. I thought the body was mapped. And when they found this, again, this is just 5 years ago, they said, oh my God, we have to rewrite the medical textbooks, the anatomical textbooks, which this is a recent image they have now begun to do. So when you understand systems, you would never imagine that something would be, in the left arm and not in the right arm. You can see this as a root or branching structure. How could it be cut off at the neck? We would know that that wouldn't make any sense, right? So that's just an idea. Some of us were, let's say, more surprised than others when this discovery was made. So that's just something from the clinical and research world that we wanted to show you in terms of understanding systems. And then the last thing that we wanted to do, because I really like to do things experientially, and I know we want to have time for questions. If you, and I think Graham, maybe I could be on camera for a minute. I'm going to take this tensegrity and I'm going to undo it. Okay. So here we've got maybe bones knocking together in a body, and somebody says, oh, I need to have surgery because these are touching and I've got pain. And then we go in and we try to either fuse things or we try to expand things. But when you start understanding systems and you understand how tensegrity works, you can take even those most distal points furthest away from where you perceive the problem to be and bring those closer together. And now you've restored that volumetric, positive win-win relationship between those pushes and pulls. Graham,
Yes.
You've got yours already put together.
Okay, let's see what I can do. There we go. You see me in the little window, or I haven't come out to the big window yet, but I will in one moment and show you the same thing as Susan made. Right,
same model. So just to feel something like that, thanks, Graham, in your body, if, for example, I had a student who was like this for a long time, he just carried his head this way. Now, we could say, get in there and push that up. Get in there and you know, squeeze something here, and that's fine. No problem. But I want you to see that if the problem is here, then you might be able to come to more distal points to the problem and instead, just shorten that other line and do that with an awareness of restoring the volumetric properties internal to the system and expanding so that you're not trying to work right where the difficulty is. Maybe you're just working outside of that more immediate area, becoming more systemic in your awareness. I think probably every one of you watching has the experience and knows about how the pain can be in the knee, but we know acupuncturists will put a needle in the ear and twist it around. And what does that have to do with the knee? The biotensegrity system, the understanding of that for our structure helps to validate, as Diane Woodruff said recently, to validate and explain that these things are not hocus pocus, that when we resolve a problem in one place by working in another, we're just working with the body's system, understanding its biotensegral aspects.
Yes, Susan. Yeah, and biotensegrity represents a different way of thinking, or the biotensegrity concept does. And we use a simple models, a simple geometry to get an understanding of how that concept applies to the human body, just to confirm what you said.
Thanks, Graham. Over to
Susan
you, Elizabeth.
Susan and Graham, thank you so very much for this captivating presentation. You so artfully put together a synopsis, a really succinct summary of a phenomenally complex field. And you were able to also bring decades of your own study to this comprehensive viewpoint. I have some questions, and questions are accumulating also. This is to both of you. And Susan, if you would start, would you speak about your collaborative and mentoring relationship with Dr. Stephen Levin, who's the originator of Biotensegrity?
Steve is very generous, and I met him, maybe 14 years ago or something. I don't remember. But anyway, after a year of study, I got to meet him. And after meeting him and just getting into it more and more, and I got into it from being a Tai Chi teacher, I sort of said to my husband one day, boy, if I had my druthers, I would just kind of drop almost everything else and just study with this guy. He's right outside of town. And my husband, bless him, said, go ahead, do it. And so for several years, I was over at Steve's house a couple days a week, and I'd show up with the idea of maybe helping him write something, maybe the book that we're still waiting for. And I'd get there and he'd have this amazing new idea, a way of expressing or showing something, a new model we had to build. And I've just found that everybody in the community really is following Steve's lead of generosity, and we're all co-mentoring each other. When I went to make out the name tags in 2015 when we had a big meeting here in DC, and I was going to put everybody's, PhD, MD, And Steve said, no, just put their names and the town that they're from. So when people came into the meeting, we were on an equal playing field. And there was no sort of sizing up somebody by looking at a name tag. Oh, that person's only a this and not a that. And that democracy, that understanding that people of all stripes have something to offer, the time in that you have as a yoga teacher or Pilates teacher or a manual therapist is just as valid in terms of personal research as somebody who's done something that's more academically or medically certified.
And Graham, your experiences with Dr. Stephen Levin?
It's very much the same. I mean, as an osteopathic practitioner, for many years, I recognized things that didn't make sense, but I never knew how to explain them. And then read an article in Osteopathic magazine described a different way of understanding the human body with a picture of the tensegrity icosahedron, and I was hooked immediately. And within a matter of days, I managed to find a route to Stephen Levin, and we communicated. And ever since, it's always been on an equal basis. We're all individuals doing our little bit, and he just was very pleased that someone was interested, and I was very pleased that someone there to help explain things and explore deeper. And we can continue doing with that, because every practitioner, movement therapist, whatever title, is performing their own, I suppose, accumulating data,
Yes.
which is then useful to their practice, to also understanding biotensegrity and vice versa.
Beautiful. This next question builds on the previous one, and again is to both of you. And Susan, if you would start off first, would you reflect on the process of a paradigm shift, the process involved in the paradigm shift from looking at human movement and human structures through the biomechanical lens, and that through looking at characteristics of biotensegrity?
Thanks, Elizabeth. Well, I was lucky, because as a Tai Chi teacher, you're not trained in conventional biomechanics. So that never was something I was concerned with. However, I've grown up in a Cartesian coordinate world of 90-degree angles and continuous compression structures. As I said in my slideshow, in Phil Earnhardt's words, this is the second way humans have ever figured out how to build. That's really huge. And when I was 13, 14 years ago, whenever I was reading anatomy trains and I saw the picture in there of a tensegrity, I knew I didn't understand what I was seeing. And so I was down the rabbit hole on YouTube with my popsicle sticks and my rubber bands and my strings and my saw. And when I finally built my first tensegrity and I felt it in my body, in my hands, I was shocked. I thought, oh my God, why didn't anybody tell us about this? This is possible. What these do physically in your hands is amazing. So I want you to know, after all these years, I still come back to this model when I have a question. Where is it in this physical structure that I can feel where I might be able to get information? I hope that helps.
Yes, and Graham, your perspective on the paradigm shift from biomechanics thinking.
Well, the paradigm shift takes us away from the old view of thinking of bones as the structure and muscles simply moving the bone. That's the way we were always taught, and it's heavily ingrained in us, and trying to get rid of those thoughts is challenging. But biotensegrity concept represents that different way of thinking, that the body is made from soft matter that functions in very different ways to what was thought of before, and it's constantly emerging. And although we've written books on it, there's so much more to find it, both individually and collectively as a biotensegrity community.
And it's a non-linear system, like love.
Yes.
You know, you don't meet your grandchild and think, well, we haven't known each other that long yet. I'm going to think about it. I might love this child. It's instant and everywhere. That's a nonlinear experience that everybody, that many people have had. And we're studying stuff like that. That's really not in the conventional descriptions of what's going on in the body, which are very linear, very mechanical, very machine modeling.
Yes.
Yes, that is a beautiful analogy. I get it immediately. And building on this same type of discussion here, would each of you speak about how you are involved in mentoring people throughout the world, and what recommendations do you have for people who are interested in developing further understanding of this field? Graham, would you start?
Well, in different ways. One of them is through the tea parties. So I'll let Susan talk more about that, I think. For myself, I have a website, Tensegrity and Biology.co.uk. I put everything I can find on there. So if anyone wants to read it, fine. If you want to contact me, just go to the contacts page, email me. I'm always happy to talk to anybody about the subject, even if we disagree on something. It's just such fun. And
It is.
it is such fun to talk to other people. And if me trying to explain something means I learn more, and I also learn something just from the question themselves, because they're looking at it maybe in a different way, but we're all in a collaboration. And there's also the Stephen M. Levin Biotensegrity Archive website, which has got so much information. And yeah.
Well, Graham, I'm going to quote you. When this question came up yesterday, you said, buy the books.
Well, okay, yes.
It's not terrible. But yeah, on the Graham and I are both on the board of the Biotensegrity Archive, and it's just dedicated to education and furthering the concept and supporting anybody who's studying it. So we're very open, as Graham said, the whole community, people are really open to talking to each other, asking questions, even if we don't agree. That's where the fun is. It's very true. We're not trying to say, I'm right, this is wrong. We're trying to say, what do we understand? Where are the gaps? Where can we go deeper? Where can we learn more? And yeah, we do have our Friday Biotensegrity parties, where tea in Biotensegrity is spelled like a cup of tea, T-E-A. You can just find that. We do them live, stream to Zoom, to YouTube, but we also do it on Zoom. And if you go to the Biotensegrity Archive website, you can get that information. And you can also get a free BX 101 guide. That's a self-study guide. That's like, 10 steps if you want to learn more about biotensegrity. And once you've done those and you've got more questions, yes, write to us. We mentor whenever we can, to the extent that we have the time to do so. I mentor a lot of graduate students who are bringing the research into their work in the sciences. So it's a lot of fun.
We have three very content-specific questions, and one from Andrew Stevenson says, Graham, what you said about how the fingers work was fascinating. Where can we read more about that? Actually, I can see there's something on page 127 of your book, but where is there more?
Well, I'm just opening page 127. Oh, yes, I see the picture there. That work comes from 2007 paper, who picked up on the anatomist Winslow, who first described this 4-bar system, and is described more in detail in my book. And since then, there's a lot of research done on movement, not specifically on the fingers that I'm aware of, but I'm constantly trawling the internet. There's just so much information to go through. These boxes here, or behind these sheets, is 3,500 scientific papers, and I get about 20 more every week, so it gets bigger and bigger reading. So contact me and we can talk about more. Read the book.
And we wrote a paper that was in the
of course.
Journal of Bodywork and Movement Therapy on closed kinematic chains, and we discuss it in there as well. You can look on my YouTube page. Just go into YouTube and put in Susan Lowell de Solo, and you'll see something on scintillating math that talks about closed kinematic chains. And specifically, Biotensegrity party number 6, we went into the superstability and the closed kinematic chains a lot. So as soon as you're ready to go deeper, all the information's there. And I think Graham's is the best website for indexing all the related research to both tensegrity and biotensegrity.
Excellent. Two more content specific questions. Chris Morita Clancy says, according to the biotensegrity model, is the cartilage at the end of bones under tension or compression?
Whoa.
On a global scale, she says.
Well, we could talk about Stopak and Harris, right? In the mesenchyme, where at that structural level, I'm just jumping in here, that which is, you've got these undifferentiated cells, and that which are under compression, those which are under compression become bone or cartilage, and those which are under tension become muscle, ligament, tendon. That's a simple way of describing it. That's research-based. What do you think, Graham?
Yes, but as the organism develops, the cartilage in the joints isn't being heavily compressed. There'll be tension and compression within the cartilage at multiple size scales, as well as every level, right down to molecular level. So
right.
The articular cartilage generally isn't heavily compressed. It acts like a cushion. So when the joints moving, a slight bit of gliding, and occasionally they might touch each other during a motion. So it designed, I wouldn't say designed, it can resist compression, but only momentary. It's the protective cushion. It's only when things go awry and you get real compression there, which becomes pathology, the cartilage wears away, the bones grind against each other, and then you get osteoarthritis and other pathologies. So
and so, Graham, the 2 points you're talking about there that I'm getting is, one is it depends on which scale level you're looking at things, right? Because everything in the body is happening at multiple scale levels.
Yeah.
So if we talk about it at one level, the pushes and pulls, the tension and compression, we may be doing that and forgetting the other scale levels that are there as well. And the other point goes back to the soft matter that we talked about. And that is a huge field that is a lot of fun to explore.
Susan, Susan, just prior to the continuation of that tantalizing promise there, let's have just a brief look at the slides on how people can order your books, and then we'll come right back to the auxeticity and the soft matter. So you will see that you can Handspring is offering a generous discount code at checkout for both books, Everything Moves and Biotensegrity, the Structural Basis of Life. And you'll note in the chat that Everything Moves is arriving in the UK warehouse next week and will be headed to the USA after that. So you'll be able to have Susan's book in your mailbox in October, providing, of course, that you have a good relationship with the U.S. Postmaster. Now, let's just take a look. You'll note, actually, that I received Susan's book in my mailbox in San Francisco, and Susan is expecting her book in her mailbox in D.C. today via Philadelphia. We can't quite understand and track that, but with a wink, I said to Susan, you have no idea how I reward my postmaster. Now, we have a second slide that just explains that our next event will be Wednesday, October 28th, which is Bridging the Neuroscience and Yoga for Pain Care. But now, back with Susan and Graham regarding the questions on the table, one of which is, can one of you provide, or maybe both of you provide, your definition of auxeticity?
Well, it's not our definition. It's the definition that physicists use, but it's omnidirectional expansion and condensation. That kind of movement, where if you think of a cake with filling and you squish down the top layer and the filling squirts out the sides, that is pushing something down, and then it gets like wider, longer, thinner this way. You could do that with a ball of putty or clay, but auxetic things will expand and condense omnidirectionally. Can I jump back to Andrew's question about the fingers for a sec? Again, I was blessed in that I didn't have conventional biomechanics for my movement training. I had Tai Chi. Everything moves is a line from the Tai Chi classics that says when one thing moves, everything moves. And when one thing is impaired for movement stops, other things stop with it. It didn't make sense with me until I felt a tensegrity. So that clarified that. And another line from the Tai Chi classics is, because we do partner work, if he doesn't move, I don't move. If he moves, I move first. Now, how do you do that? It defies logic. However, if I'm connected to somebody in system, then when one thing moves, everything moves. To somebody who is expecting a response that goes through the nervous system, it may indeed seem like I'm moving first when they move. And we know, think of it from experience, how much you have done something where the nervous system would arrive too late. Anybody who's done any sports, I remember kind of catching and throwing a Frisbee and in the middle of a game and that sort of thing. And it's over before your conscious mind is on the scene. There's a lot of that going on in the body that we don't understand yet.
Graham, your perspective?
Well, I go along with what Susan said, but all for the technical people, and I'm one of those, auxetic behavior represents a negative Poisson ratio. And what do I mean by that? Well, if you take a rubber band, elastic band, and stretch it, it gets thinner in the middle. And when you shorten it, it gets fatter again. And auxetic behavior, the elastic band is performing a positive Poisson ratio. Auxetic behavior does the opposite. So when we lengthen it, the structure gets bigger in the middle, thicker in the middle. It exhibits what's called a negative Poisson ratio. This is for the mathematicians and technical people. So auxetic behavior is a great name to describe what's happening. And it's only been known about for 30, 35 years. It was considered impossible before that. And now there's a lot of work to produce engineering, technical things, value to it. A lot of living structures behave auxetically. It's now confirmed. There's so much evidence to support it, which is why we have to think about during treatment, when we've got our hands on or describing movement, we have to look at it in a different way because it's a different way of thinking. Okay, Elizabeth.
A question from Rachel Tudor. Can you speak to transmutability in biotensegrity?
Ooh, transmutability, as in changing from one thing to another.
Well, I think the easiest way, the easiest way to look at this is as a soft matter issue. So conventional biomechanics models the body as if we're made out of, well, think of it, solid, liquid, gas. There are college websites today that say there are 3 kinds of materials, solid, liquid, gas. Actually, there's a huge category of material that falls into none of those 3 categories. That's soft condensed matter. And a nice, fun, easy way to play with it is to make some oobleck, OOBLECK. Just check that out on YouTube. It's a cornstarch and water mixture. And when you put your fingers into it, it feel like you're dipping your fingers into milk or something. But if you make a fist and you punch it fast and hard, your fist bounces right off. The material itself, this is inert material. This is without the intelligence of an organism, right? The material itself jackets and changes its characteristics according to what you physically, according to the forces that are coming to bear on it.
And the tissues inside are doing the same thing all the time, transitioning from one phase to another all the time.
Exactly.
Susan and Graham, have you summary comments? That's a tall order.
Mine is this: you got to build one of these, guys. If you haven't built one, then it's going to be really difficult to know what we're talking about. I have a thing on YouTube called Collapsible Tensegrity, and you can build one with non-stretchy strings. So the elastic models, there are some wonderful models out there of spines and pelvises and stuff like that, and those are really great. You're at one hierarchical level in the system, at one hierarchical level maybe in the system, one scale level, and what you need to understand is the movement that's happening on multiple scale levels. So if you've got a stretchy one, that's great, but now build a conventional tensegrity.
And in the process of building it, you'll find that you pull one string and everything moves, the whole system. So if you're trying to get it, all the struts are lined up perfectly, you pull one thing and it changes over here and now over there, and you wonder what's going on. But it's only when you play with it physically, you appreciate these things, and it'll transform your outlook, the way you look at the human body.
Then you can learn through your fingertips instead of through reading.
Yes.
Or we can learn both ways. Really looking forward to repeated deep dives into the oobleck. No, into your books, into Everything Moves and Biotensegrity. I was just imagining, Susan, the oxyticity of the experience of immersing in Everything Moves and Biotensegrity. Thank you both for your really exquisite presentation to clarify the complexity of this field. We look forward to being with you on Fridays at the Biotensegrity parties and to repeated conversations, new conversations regarding the treasures in your books.
Thank you, Elizabeth.
Thank you so much.
Thank you. Bye.
Bye.